All right, welcome to another video. In this video, we'll be looking at the polar form of a complex number. So let's get right into it. So last time, in the last video, we looked at the complex plane. So we can associate different complex numbers as a vector, right? We have the real part of z and then the imaginary part of z here as well, okay? So if I have a complex number z, a plus bi, we can associate that number as a vector. Okay, so we can associate with that as a vector whose components are a and then b, right? So this is our complex number z. So to get in polar form, the polar form of a complex number, we want to use right triangles. So we can draw in a right triangle like this. And then to figure out the x and the y components of this right triangle, we can use trigonometry. So this would be the argument of the complex number, theta. And then the magnitude is just r, right? So r, by definition, is the square root of a squared plus b squared. And then theta would be the inverse tangent of b over a, right? Y over x. Okay, so to get also the x and the y components of the complex number, we can just use trigonometry, right? So the a component would equal to the hypotenuse times cosine theta. And then the b component would equal to r times sine theta, right? So therefore, to write out the what's called the rectangular, so this form is what's called the rectangular coordinates of the complex number. This would be the polar form. So a is r cosine theta, r times cosine theta, plus, I'm going to write it out like this. I times b is r sine theta. Okay, so this here is the polar form of a complex number. Okay, polar form of a complex number. In Calc 2, you may have seen this type of formula appearing on the right. And it refers to Euler's identity. Euler's identity, I'll say. Right? E to the I theta is equal to cosine of theta plus I sine theta. Right? This was derived back in Calculus 2, where we had to look at the Maclaurin series, of e to the x, right? E to the x. And that was 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. And then you're going to look at this quantity, e to the I theta. So that means you're going to plug in I theta where x appears in the Taylor series, right? So it will look like this. I theta squared over 2 factorial plus I theta cubed over 3 factorial and so on, right? And just remember that I squared is -1 by definition, right? And this is a good exercise for you to work with. So you want to try to manipulate this right-hand side of this equation, and then you'll get Maclaurin series for cosine of theta, and then the Maclaurin series for sine of theta, and you'll arrive at this conclusion, right? But so we can actually write out z as r times e to the I theta, This is just another way to express a polar form of a complex number. Okay, so that's another way to express it. So for example, let's look at right. So if I have these examples, 1 plus I and minus 3I, let's say, right? Try to work on these examples and see what you come up with. Okay. All right. I guess you were looked at these examples and worked on them on your own. And let's see what we have. So 1 plus I, this is 1 unit in the real direction and 1 unit in the imaginary direction, right? So so it would be this vector, right? 1 plus I, right? So the real part is 1 and the imaginary part is 1. Okay. And so what we want to do is figure out what R is. R is equal to the square root of 1 squared plus 1 squared, which is root 2, square root of 2. Theta, on the other hand, we want to look at the inverse tangent of y over x. So in this case, 1 over 1. Inverse tangent of 1. What is that? If you guess pi over 4, you're right. It is pi over 4. So we can write out z is equal to root 2 times e to the I times pi over 4. That's the polar form of a complex number, right? Or you can write root 2 times cosine theta plus I sine theta, right? That's the other way to do it. Now here's the other example. Minus 3i. This one's a little bit tricky, but here's our complex plane. Right, here's our complex plane. And we want to look at, so this is minus 3i here. Minus 3i. Well, what's the radius? So the radius, the real component is 0 and the imaginary component is minus 3. So it's the square root of 0 squared plus minus 3 squared, right? So which is 3. The radius is 3. And then theta is equal to inverse tangent of minus 3 over 0. Uh-oh, that's bad news. But, you know, inverse tangent of just any theta, well, it's in between minus pi over 2 and pi over 2, right? Okay, so clearly this is minus pi over 2, but we want the angle that fits this quadrantal angle. That's what it's called, right? The quadrantal angle of minus 3i. So in this case, theta is 3 pi over 2. Okay, so z is equal to 3 times e to the I times pi over 2. 3 pi over 2, excuse me. Okay, hopefully that made sense. All right, 3 pi over 2. So we're going to get into, with sine and then cosine, they are periodic, right? So if you have one angle in the complex plane, and if I add 2 pi, I'll get the same angle, right? Keep adding 2 pi, and then if I also subtract by 2 pi, I also get the other representation of that same angle. So what we need to do is we're going to make what's called a branch cut. And this will be common in the next couple of sections. So we're going to look at a branch cut of the argument, and this is what's called the principal. The principal argument. Since we have periodic angles occurring, right, we want to define, we want to have a well-defined function for calculating our angles, right? And the principal argument of a complex number will do that. Okay, so it's labeled as capital ARGZ. Okay, this is what's called the principal argument, and the range is it's greater than pi or minus pi. So the principal argument is greater than minus pi, but it's less than or equal to minus pi radians. So on the complex plane, so minus pi would be an angle that's clockwise. So we're going to start along the minus real axis, and then we're going to go this way, right? And that's how we define the principal argument of a complex number. So this is the real axis and the imaginary axis. Okay, and this is what the range is that we're referring to here. Okay, so as an example, if I have this complex number, z is equal to minus 3 minus, I'm sorry, minus 1 minus I. Minus 1 minus I. Okay. So that complex number corresponds to a vector in the third quadrant. So it's down here, right? So z right here, minus 1 minus I, right? And so what we want is the principal argument, right, of this complex number. So our range is in minus pi here to pi, okay? So in order to do this, all we have to do is look at the so okay, yeah, all we have to do is look at its reflection, right? So it would be 1 plus I, right? 1 plus I. Calculate the angle for this complex number. So theta in this case would be pi over 4. And then we're going to take this angle and subtract it by pi radians, right? If we subtract an angle, we're going to go clockwise. So just take pi over 4 minus pi radians, and that would be this angle right here, but it's negative. So it's the clockwise representation of z equals minus 1 minus I. So that would be minus 3 pi over 4. Okay. Remember, the range for the argument of a complex number is in between minus pi and pi. Okay. So minus 1 minus I, so its principal argument would equal to minus 3 pi over 4. Okay. So that's the principal argument. Hopefully that made sense. Okay. So there's also different operations of complex numbers in polar form, right? So if I have So if I have two polar equations of complex numbers Z1 and Z2 written out like these respectively, e to the I theta 2, right? Then Z1 times Z2, well, that is equal to R1 e to the I theta 1 times R2 e to the I theta 2, right? And then we're just going to use properties of exponents to combine the exponentials here, right? And then what this equals to is R1 times R2 times e to the I theta 1 plus theta 2. Okay. Or to write out the cosine sine counterparts, cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. Okay, so we multiply the radii of each complex number and we add their angles. Okay, pretty straightforward. Part B, Z1 divided by Z2, this would equal to R1 e to the I theta 1 divided by R2 e to the I theta 2. So this time we divide the radii and then we subtract the angles. So this will be e to the I theta 1 minus theta 2 using properties of exponents. And so this equals to R1 divided by R2 cosine of theta 1 minus theta 2 plus I sine theta 1 minus theta 2. Okay. All right. Okay. So as an example, find Z1 divided by Z2 and Z1 times Z2 when Z1 equals to 2 times cosine of pi over 8 plus I sine of pi over 8. And Z2 is equal to 4 cosine of 3 pi over 8 plus I sine of 3 pi over 8. These should be parentheses here. Okay, so I'll give you a few minutes to work on this example right here. All right. Okay, so I assume you worked on it. So let's actually look at what these numbers would look like in polar form. So Z1 times Z2. So we have to multiply the radii, right? So 2 times 4, and then add the angles. Cosine of pi over 8 plus 3 pi over 8 plus I sine of pi over 8 plus 3 pi over 8. Okay, so this equals to 8 times cosine of 4 pi over 8, which is pi over 2, plus I sine of pi over 2. Cosine of pi over 2 is, yes, 0. And then sine of pi over 2 is 1. So it'll be 0 plus I, right? So this is 8 times I, right? Okay. So in polar form, this is 8 times e to the I pi over 2. Okay. E to the I pi over 2. Okay. Division, Z1 divided by Z2. Well, it's just 2 times cosine of pi over 8, 8 plus I sine of pi over 8 divided by 4 times cosine of 3 pi over 8 plus I sine 3 pi over 8. Okay, so this equals 2 over 4 times cosine of pi over 8 minus 3 pi over 8 plus I sine pi over 8 minus 3 pi over 8. Okay, so this equals to 1/2. So this is cosine of minus 2 pi over 8, which is cosine minus pi over 4 plus I sine of minus pi over 4. Okay. All right. So this will be 1/2 times root 2 over 2 minus root 2 over 2 times I. Okay. And so this equals to, in polar form, e to the I minus pi over 4. Okay. Nice. Okay. The last thing I want to talk about is a very important property on powers of complex numbers, and it's called de Moivre's formula. It's French, and I apologize for my French. So de Moivre's formula. Okay. So for a integer power, n, z to the n is equal to r to the n times cosine of n theta plus I sine of n times theta. So and okay. Yeah, so this would hold for any integer. Yeah, any integer. Okay. So yeah, any integer power. Okay, so for example, right, if I want to compute this following number in polar form, right? Well, first, it's a lot easier to convert 1/2 plus 1/2 I in polar form, right? In polar form. And notice here, the numbers 1/2 appear the same in the real and the imaginary components. So they will produce the angle of pi over 4 radians, right? So they lie on the line y equals x, right? And so if your real and your imaginary components are equal, that means your angle is always pi over 4 radians. Okay, pi over 4 radians. So really, all we have to do is compute the radius, right? The radius, or the magnitude, I'll say. The magnitude is 1/2 squared plus 1/2 squared, right? And so this equals to 1/4 plus 1/4 is 1/2. So you'll have This is the square root of 1/2, right? So root 2/2 is the radius. Okay, so this in polar form, this is root 2/2 e to the I pi over 4, right? And so we can replace that inside the parentheses, right? Okay, so we exponentiate the radius. Okay, so this equals to root 2/2 to the 10th power, and we multiply the angle by 10. 10 times pi over 4 plus I times sine of 10 times pi over 4. Okay. And so, okay, so if I write out, so we'll have the square root of 2 to the 10th power, that's a ginormous number. And then we'll have cosine of 5 pi over 2 plus I sine of 5 pi over 2. Okay, so 5 pi over 2, that's 1. So we'll have okay. So if I write this out as 2 times 5, okay, so really it's just 2 to the 5th over 2 to the 10th here. And then we'll have e to the I 5 pi over 2. The principal argument is pi over 2. So we'll have 1 over 2 to the 5th, so 1/32. 1/32 times I, right? Times I, or 1/32. The principal argument is e to the I times pi over 2, right? So these would work. And then this is the rectangular, and this is the polar. Okay, so hopefully that made sense. Here's some problems to check comprehension. So we have 4, 6, 11, 12, 18, 20, 23, 30, and 49. Try to work on these problems. And if you have questions, leave it in the comments. And in the next video, we'll look at powers and different roots of complex numbers. So thanks for watching, and I'll see you in the next video.